All right. So the first set of reactions that we're going to cover are here. Reactions of, I don't know why this 36 is on here, but ignore it. Reactions of alcohols. And so with alcohols, I don't know why that's there. So with alcohols, you can do a couple of different things. You can do ester synthesis, which is what both of these reactions are. Or you can do ether synthesis. And we're going to talk about both and how they happen. All right, so I'm going to cut this. And then let me add a page right quick. We're going to talk about that top reaction. All right, so with the transesterification, you've seen this reaction before. When we did aspirin synthesis, we just used a different esterification agent. But when we did aspirin, we actually took salicylic acid. And we reacted that with acetic anhydride, which is this, right? And then we converted this alcohol right here into an ester using acid, H2SO4, as the catalyst, right? And then so the end product, you end up with that alcohol becoming esterified. So it's O, right? So we've seen this before, right? This is an example of transesterification, right? But another way to make esters is to take alcohols and react them with carboxylic acids. All right, so let me move this here. So we have this alcohol that we have shown above, plus any generic carboxylic acid. I'm just going to put an R. And it has here that it's in the presence of an acid catalyst, right? And so what that acid catalyst does is it activates the carbonyl. And I'm going to show you how that happens in the mechanism. Right? So the acid catalyst is going to activate your carbonyl, and then you end up with an ester plus water. Right, so it's like a condensation reaction. All right, so the first step, I'll put some lone pairs here. The first step is going to be a proton transfer from the acid. So we got this plus right now that oxygen becomes positive. Anytime you have acid or some acidic source around oxygen, it's going to protonate oxygen, right? So the oxygen is now protonated, and then so once you do that, So now that you do your proton transfer, and then after that, that's when your alcohol oxygen is going to attack your carboxylic acid, right? So you attack, and then you get this intermediate that we even talked about this when we were doing granular additions to carbonyls, right? Where you get this tetrahedral intermediate. Right, so your alcohol is acting as a nucleophile, and all of these reactions are the same in that alcohol is going to be a nucleophile, right? So it's going to attack some electrophile. So now let's see what we get from that. We get this tetrahedral intermediate here. All right, and then the alcohol is still protonated. So that's positive. All right, so then you get another proton transfer because you need to get rid of the proton that's on the alcohol. So let's take this oxygen right here, and let's do the proton transfer to that one. All right, so you're doing an internal proton transfer, or intramolecular proton transfer. Do something, fix this really quick. It's intramolecular. Right? Does anybody know what that term intramolecular means?
Is it between molecules?
Well, it's within the same molecule. Between, I'm glad you said that though. If it was between two different molecules, it would be intermolecular. So intramolecular, that's internal. And then this is that's external, right? So if like right here in step one, the alcohol attacking the acid, that's intermolecular. But when a reaction happens within a molecule where there's no external reagents coming in, then it's intramolecular. All right, so we are here, and then now we have water, which is an excellent leaving group. Right, so I can now kick that out. Right, so now that gets me to this version of the ester. It's not the same, it's not the final product, but we're close. And I'm gonna put down here plus conjugate base. All right, so how do I get to the final product, the ester, which I have drawn up here? What do I need to do? Anybody? How do I get to this? from this? What do you think?
Deprotonate.
I need to do another proton transfer, right? I can use water, but remember in the first step, you did a proton transfer from an acid catalyst. So what's left from that acid is the conjugate base, which I have shown down here, right? So that conjugate base can do proton transfer and then also regenerate the catalyst, right? At the same time. So I'm just going to show that. Let me erase this box. I'll show that happening. Hold up. It's up here. Right, so that final step is always going to be another proton transfer. So it's going to be proton transfer with the conjugate base. Right, and what that does is it regenerates the acid. So when we say the acid is a catalyst, what do you know about a catalyst? Does it ever get used up?
No, it regenerates.
It always regenerates. Right, so that proton transfer with your conjugate base is going to regenerate the acid catalyst, and then you can start the reaction all over again. You can do another proton transfer on another carboxylic acid and start again. Right, so you got proton transfer, alcohol attack, an internal proton transfer, and then elimination, which is what this step is right here, where you lose water, and then a final proton transfer to get you to your ester. It's a long mechanism, but all of it is either acid base or nucleophile electrophile chemistry. It's all stuff that we already know. Now it's just applying it. All right. Any questions about that? All right. The acid chloride version of this is much easier, much shorter mechanism too. So let me pull that down right quick. All right. No questions about the ester formation. All right, I think I can fit that here. So there's no catalyst required for using an acid chloride to make an ester, right? The reason is because the acid chloride is so reactive that you really don't need a catalyst. It's like for acid chloride, I say this every time I teach this section. When you take the cap off the bottle of an acid chloride, you can see the vapors reacting with the water in the air, right? So it's a super fast reaction, probably preferred actually. So let's see what happens. So here's my alcohol, and I'm going to react that with this acid chloride. Again, the first step is going to be nucleophilic attack. of your alcohol. Right? Every time. So this is going to attack here. And you break the CO pop bond. All your carbonyls are going to react the same way with a nucleophile. Anytime you react a carbonyl with a nucleophile, you're going to end up with the tetrahedral intermediate. And that intermediate is either going to get quenched or it's going to break down and eliminate something to get you back to the carbonyl. So one of those two things is going to happen every time you react a carbonyl with a nucleophile. So you're going to end up with this tetrahedral intermediate. Right? All right. So the tetrahedral intermediate in this case is going to collapse and eliminate. So step one is going to be attack of the alcohol. And then step two is going to be the elimination of chlorine. Right, so you're going to lose chlorine as a leaving group in this case. And then in doing so, you're going to reform the CO pi bond. So you end up here. So now your chlorine can just do a proton transfer. Sometimes this is done with a base present, like pyridine or something like that, to activate your alcohol, but this mechanism is also plausible. So you can go in and do a proton transfer here. And then that'll get you to your product, which is the ester. I know on the handout, I'm gonna fix that before I upload it actually. It says plus H2O, but there's no water lost here. So I'll fix that before I upload it to Blackboard in the course notes section. Any questions about the acid chloride mechanism? Again, the esterification, all we're talking about is ways that we can use alcohol and react alcohols. So one way that we can use alcohols is to make esters. Right, that's one of the uses of alcohols. All right. The other way, the other reaction up here dealing with alcohols is the synthesis of ethers. So let me grab this. Right, and so the ether synthesis is is shown here. Right, everybody should remember what an ether is from part one. So it's a I'm just going to give you a generic version. Right, so an ether is a functional group where you have an oxygen with a single bond of carbon on each side of it. Right, they're not very reactive, but you know it's a pretty ubiquitous functional group. You find ethers everywhere. You can have a acyclic ether like dimethyl ether, or you can have a cyclic ether, something like this, right? This is an epoxide. But ethers are very common functional groups. All right. So the way you make them is actually pretty simple, right? You can see here, and we've seen this reaction before. You have an alcohol, you have an alkyl halide, and you use a strong base, right? And that base is needed because you need to make the OH group a better nucleophile, right? So the base here in this, what we call Williamson ether synthesis, is, let's see if I can grab this again, move it down. So the Williamson ether synthesis that's shown, again, you have a alcohol, you have an alkyl halide. It's a simple SN2 type substitution. Right? It's a very simple reaction. So the way that this works, again, you have your alcohol, you're going to deprotonate it with the base. That's always the first step. And the way you would do this in the lab, more than likely, you'll stir your alcohol with the base, and then you'll syringe in your alkyl halide at low temperature, right? So here's your alcohol, and we're going to react this with the hydroxide anion, right? So that's going to come in, pop that proton off. Let me fix this up. You're going to give those electrons back to oxygen. Again, the simple acid-base chemistry right here. And then you end up with this oxygen plus water. And then when you react your alkyl halide, let's just say CH3Cl, right? Or let me draw it out. Right, it's a simple SN2 type substitution, right? Where you take the negatively charged oxygen and attack carbon. So the first step, proton transfer. Second step is nucleophilic attack. And so you end up with an ether. Right, you started out with sodium hydroxide. That sodium is going to end up with chlorine. So that's where the NaCl is coming from. And then the water from the first step. So the main product is here. It's the ether. I don't care about anything else. I just care about making the ether. All right. Any questions about the ether formation or the esterification? All right. So I know
Wait, so
go
for
ahead.
that question above,
Mhm.
you were getting the R, but you were just showing us how to make it either. Like it wasn't related to that question.
So it's related. The R can be anything, any carbon containing group.
Okay.
So when it says an alkyl halide, R can be any alkyl chain. It can be a 4-carbon chain. It can be but it doesn't matter what the R group is. It's just an alkyl group.
Okay.
So in the example down here, I just chose to make RCH3. Right, but that when you see R like that, that's just a generic descriptor. All right. Any other question? That's a good question. Any other question? All right. Anybody still writing this down?
Yes.
All right. I'm gonna leave it up. I'll leave it right here for a second, and then I'm going to look at those carbonyl, the oxidations of alcohols, and then we're going to stop and deploy the exam so y'all can work on that. All right. Just let me know when you're done writing.
Okay, you good. Thank you.
All right. So let's go back to here. And here you have three different alcohol oxidation reactions, right? We're not going to go through the mechanisms for these because those mechanisms get pretty complicated. Suffice it to say, let me just show you in general what happens when you oxidize alcohol, all right? This is not meant to be very precise, but it's just a way of thinking about it. So if you have an alcohol like this, so this is just a general idea of what happens in an alcohol oxidation. I should probably not put that down here. Actually, let's do this. Pull all this down here. And I'm gonna paste this down here. Give me 1 second. All right, so for alcohol oxidation in general, what you're doing is removing, right? So for any oxidation, and when we talk about oxidation in terms of organic chemistry, one of the things you have to think about is it's different from in G-Chem when you learned about oxidation and reduction, right? In G-Chem, when you learned about oxidation, you learned about losing electrons or gaining electrons. In organic, oxidation is either loss of hydrogen or gaining oxygen, right? So all these oxidations you are in essence gaining oxygen. When I say gain oxygen, that could also mean increasing the number of bonds to oxygen. Right? Because if you look at the examples, you didn't gain an actual oxygen. You actually made carbon and oxygen go from a single bond to a double bond. So oxidation can also mean the increase in the number of bonds to oxygen. So in general, if you have a alcohol, let me do this different. Right, what you're doing is in essence losing H2, right? Because you're going to lose this hydrogen and you're going to lose this hydrogen, right? So you end up with a carbonyl. Right now, how that happens is going to depend on what the reagents are, right? If you use transition metals, sometimes it'll happen through some type of insertion and reductive elimination, or if you use like a reagent like the Swern, you do a different type of elimination, right? But in the end, you're going to lose a hydrogen from the carbonyl carbon, and you're going to lose the OH proton, right? Right, so you're gonna lose both of those in order to oxidize that alcohol up to a carbonyl. So you can see right here in this first reaction, you have a primary alcohol, right, and you can react it under either Swern conditions, and I'm gonna pull that up too so you can see the reagents. It's like oxalochloride and DMSO, I think, but I'll show you the conditions in a second. So you can do a Swern or you can do chromic acid. Both of those take primary alcohols and convert them into aldehydes, right? So you can see right here where it says primary alcohols are going to form aldehydes in the product. Because remember, if it's primary, you got two hydrogens right here. All right? So you got two hydrogens there. So primary alcohol is going to give you a aldehyde. And the reagents that you can use to do that, you can use a Swern oxidation, or you can use chromic acid. Let me pull up the Swern right quick, and I'll show you organic chemistry portal. This is a great website, by the way. Organic chemistry portal. Every reaction that has a name is on there, and papers as far as where it was applied, where the reaction was applied, all of that. So let me search Swern. Come on, autocorrect. I know what I'm talking about. Oxidation. All right, so for the Swern, again, it is DMSO, which is shown here. Let me annotate this if I can. Maybe not. All right, so you got DMSO. Let me see something right quick. And then oxalochloride, which is the compound on the right with the two carbonyls, and then a base. right? So the first, and the mechanism is down here, right? So the oxalochloride and the DMSO react to give you this dimethyl chlorosulfonium ion, which is shown here on the right. Let me how can I annotate this? Let me see if I can annotate it. So this is your reactive. Can y'all see my drawing on the screen?
Yeah.
Okay.
No.
So that dimethyl chlorosulfonium ion, that's what the reactive species is in the SWRN, and that's what's gonna when you react with the alcohol, that's what's gonna activate your alcohol and oxidize it, right? And you can see in the first step, you lose HCl, so now you've lost the OH proton. And then in the next step, you lose the carbonyl proton. You can see that too right here. That's the purpose of the base, the nitrogen base that's right here in the second step. All right, so that's what so you lose your OH proton and then you lose your carbonyl proton. And then after that, losing the carbonyl proton, now you can see here you eliminate sulfur also, right? So then you end up with your carbonyl plus dimethyl sulfide. And you have to do this at low, so SWRN is done at low temperature. It's done at negative 78, right? So the concept of alcohol oxidation is going to follow. It's going to follow that same basic paradigm where you lose the OH proton and you lose the carbonyl proton in some type of elimination to give you a excuse me, a carbonyl. All right. If you look at the secondary alcohols, which is shown here, there's a set of reagents for secondary also, and it's TPAP and NMO. TPAP is tetrapropyl ammonium peruthenate. Right, it's a ruthenium type. It's a ruthenium catalyst. Right, so TPAP is and followed by NMO, which is a co-oxidant. You use that for secondary alcohols. Right, doesn't really work well on primaries, but on secondaries it works well. Right, so if you start out with a secondary alcohol, you can see that you're going to get a ketone in the product. Right, if you use a tertiary, it's not going to work. Why not? This would be an example of a tertiary alcohol. Why can't we oxidize the tertiary?
Is it because it's hard to attack the carbon?
Think about, okay, it does have something to do with the carbon. If you look at the carbon, let's go back up to here. What do I need to lose off that carbon? I need
hydrogen.
Hydrogen.
Mm-hmm.
And if you look at the tertiary alcohol, does it have any hydrogens on the?
Yeah,
carbon?
it's completely full.
Yeah, it's full. So there's no carbonyl proton. So we can't lose it. So we can't do an elimination. Right, so if it doesn't have a carbonyl proton, then we can't eliminate. So a tertiary alcohol you cannot oxidize. Right, there's one other oxidation of alcohols that's shown here with potassium permanganate, and that will not stop. Right, that's what we call a superoxidant. It'll keep oxidizing the alcohol all the way up to the carboxylic acid. So this is this oxidation state for carbon, where you have 3 bonds to oxygen. We call it the ester oxidation state. Right, that is that's carbon having 3 bonds to oxygen, so we call it the ester oxidation state. All right, so that's higher than a aldehyde or a ketone, so it's a higher oxidation state, right? The potassium permanganate is another type of catalyst, and is like super aggressive when it comes to oxidizing alcohol. So you're not going to just stop at the aldehyde, or if it's secondary, secondary is going to stop at the ketone, but a primary, it won't stop at the aldehyde. It'll keep oxidizing until you get up to the acid, which is in the higher oxidation state. All right, we're going to stop here on Wednesday. I'm going to have another worksheet that we're going to be working off of, so we can start seeing some of these reactions in practice. But for now, we're going to stop with the alcohol oxidation, and then esterification and etherification. We'll stop there. So I'm going to upload this handout to Blackboard. I'm also going to open up the 2 assignments that we're going to be doing for this section. All right, anybody have any questions about anything before we stop? All right. So we're gonna, is anybody still writing?
What did you say at the beginning of the class? I came in and you were talking about making a link for you to turn in old assignments or something.
It's already made.
No, I was just asking, is that what I heard correctly?
Yeah.
Okay.
Yeah. I was just saying I'm not gonna open up the assignments. That's why I sent out the OneDrive link.
Okay.
So you can turn in what you're missing in that folder. But I'm gonna send it out again. When I send out the announcement, I'm gonna send that link out again, just in case somebody didn't get it or somebody's still confused about what to do.
Okay.
All right. All right. So I'm gonna stop the